continuing the internal and external seminars. So today's talk is by Shachar Lovett from here. And tomorrow's talk will be Tony Ampatasi from the University of Toronto.
Thanks. Great, so I'm going to speak about polynomials and Gaussian variables. So let me just define what the setting is. So we're going to have a polynomial, f of x1, of xn. It's going to be a real polynomial of degree d. And for this talk, let's think of d as some constant. So I'll ignore factors that depends on d and like O terms, stuff like that. I think of d as some constant. And the question is, well, what is the distribution of f? What is the distribution of f? Well, we need to assume something about the input distribution. So let's assume the inputs are Gaussians. And something can be, if what I'm saying here can be generalized to other distributions. I'm not sure if there are any interesting distributions it generalizes to. But let's just say under Gaussians. And that's, well, this defines a family of distributions. All these distributions coming from low-degree polynomials. But that's still not a very well-defined question. What do I say about, what can we say about this distribution? So let me give you two specific questions that people have studied a lot. And one, so here are some specific questions. So one is about the tail. I guess a tail. So what's the probability that f of x is larger from t when t is large? So unless I specify distributions, they're all independent star non-normal, and x, I just mean, so x will just be x1 to xn. Okay, so that's one question that people have studied a lot, and the other one will be about concentration. Which is just the opposite. So what's the probability that f is very small, or let's say very close to some specific point? Where epsilon is small. Okay, so those are two specific questions. And so those two types of questions were usually studied from people in functional analysis using things like the normal distribution is a low concave distribution, and you can use a lot of geometric interpretations about low concave distributions. So just a little bit of history, and I'm sure I'm missing some of it because I just learned about some of it in the last few days. So for log concave distributions, so I guess there were various works which gave very good, or almost tight, both upper bounds and lower bounds. So that's, I guess, the works of Bourgain and Kanan, Lovash, Shimonovich, who gave a very neat geometric way of reducing things from n-variate distribution to just a single-variate distribution, to one-dimensional problems. And then those were used, I guess, by, or similar ideas were used by Nazarov, Volberg, and Sodin, and also by Carbery and Wright. Again, so all of those authors study in general low concave distributions and give very good bounds on such questions.
The tail or the anti-concave?
So actually both. So a lot of them were about the tail, but some, so let's say both Nazarov Sodin and Carbery Wright, and even this, so this not explicitly, but they speak also about the concentration around zero. So they reduce the problem from n-variate to a single variate, and for a polynomial in one variable, we know a lot. So you can use any result you have there and lift it to n variables. And again, all this with the fact that your distribution is low concave.
So you mean the original distribution, then you're talking
Yeah,
about polynomial.
exactly, the normal distribution of the variables. So just
For Gaussian and tail, it's older, right? This is probably the easiest of the four possible. I mean,
so which one?
Gaussian.
or for the tails.
Yeah.
So it depends. So if you want to get, I guess, very good tails, you need to use something like the hypercontractive inequality, which gives you something like e to the minus t to the 2 over d. If you just use low concave, actually the answer is 1 over d instead of 2 over d. So actually, I think I'm not sure which one came first. Anyway, I was interested in this question because it has various applications in computer science for polynomial threshold functions, which are just signs of real polynomials. And some of the question was, can you prove, let's say, so today I'm only going to speak about this concentration problem. Can you prove it using some combinatorial method that wouldn't use the fact that this normal distribution is low concave? Maybe use some other properties of it. So my goal today is to show you a different proof of how to get concentration bounds. So let me just tell you what the real answer is, and then what I can show using some more combinatorial methods. So I guess I should let's write it here. So let's start with just something simple, some example. So to get what we might hope. So if we ask what's the probability that just x, let's say x1, is at most epsilon, where x1 is just normal. So that's just the simplest normal, just take a normal variable. Well, we know that's just order of epsilon, because the normal distribution has a constant density around 0. Right? And well, similarly, if you ask what's the probability that x1 to the d is at most epsilon, that's a very simple degree d polynomial, right? Well, that's, again, order of epsilon to the 1 over d. Right? So the best we can hope for concentration is order of epsilon to the 1 over d for degree d polynomials. We can hope for better than that, at least not for general polynomials. And it turns out that that's really the answer. So that's a theorem of, I guess, let's just state the Carbery Wright version. So can anybody see here? Yeah, okay. So, well, for every degree d polynomial f, and we need some normalization, right? If we multiply f by 10, then all things here grow by 10. So we need some normalization, let's say the variance of f. So let's say the variance of f is 1. So the probability that f of x is below epsilon is order of epsilon to the 1 over d, and there are some constant depending on d here. So in their version, it's d. I think in the version of Nazarov, Wahlberg, Sodin, there is no constant here.
So what is the variance of f?
Okay, good. So that's a very good question. So okay, let's just do this an example. Okay, let's just put it here. So there is a case where the variance of f is very simple. So let's assume f is multilinear, which means in every monomial, each variable occurs with degree at most 1. Yeah.
So did you mean how do you compute it, or what is the definition?
Oh.
Okay, good. I'm gonna. So the variance of f. So let's assume that.
Not the variance of f of x.
Yeah, I just mean the variance of f of x over normal distribution variables. But I want to give some explicit formula.
But you can.
But there are a very simple explicit formula, at least when it's multilinear, and also a very relatively simple when it's not multilinear. So assume that the polynomial, so your sum is over sets of n variables whose size is at most d. You have some coefficient, and then you multiply all those variables, xi, I in I. Okay, so that's a multilinear polynomial. Not the most general polynomial, because every variable occurs with degree at most 1, but it's still general enough. So what's the variance of f? So let's see, what's the average of f? Well, that's just the free coefficient, right? That's just. And what's the average of f squared? Well, those are normal variables. So if you multiply any two monomials, their average is 0, unless it's the same monomial multiplied with itself, right? So just the sum of fi squared. So the variance of f is just the sum over all I, not the empty set fi squared. Okay? So when it's not multilinear and you have some degrees here, then you need to ask, okay, what's the moments of the normal distribution, and those enter into the computations here. So you'll get something here which depend on the moments. But that's some simple formula. Okay.
There's actually a trick that lets you reduce the multilinear case in general.
You can decopies of each variable.
Because you can replace, if your boundaries depend on n, you can replace x1 with like sum of like a zillion Gaussians divided by root a zillion.
Okay.
And when you like expand it out, like anything that occurs with a higher power will have like negligible variance compared to the multilinear term.
I see.
Anyway, it's not.
It's just a very small technical point anyway. You can handle the non-multilinear case in the same way.
Yeah,
It's just here you just don't need to ask what are the coefficients. Okay. So again, so that's the variance of f. And so they really show it using the assumption that the Gaussians are long concave and using geometric interpretation. And this talk and what I'm going to show you, so maybe I'll just write it smaller. So let's do it here. So they really get the right answer. We're not going to get the right answer. But we're still going to get some polynomial dependence on epsilon. So in this talk, I'll show you under the same assumptions that the probability that the absolute value of f of x is at most epsilon is order of epsilon to something like 1/4 to the d, which is very far from the right answer. But on the other hand, this can also work for discrete distributions of various sorts and so on. So we don't even assume that the distribution is smooth. Okay. And the proof will be very simple and very combinatorial. Okay, so are there any questions about what we're going to show? No. So since I claim the proof is simple, I hope I'll be able to show it in, say, 30 or 40 minutes. At least to try. Good. So there will be two steps to the proof. The first step will be reduction to a simple, nice polynomial. We set multilinear polynomials. This will just use convexity. The second step will be to argue there and just use simple induction on the degree. So what are the proof steps? Yeah, sorry.
So you can also show anti-concentration around any point, and it's also bounded by epsilon to the 1?
Yes, because you can take f and shift it by anything, and the variance doesn't change.
With f, it's not an issue.
Yeah, so the variance stays the same.
Also, when we spoke, I asked you why can't you use Chebyshev like
Okay.
all these bounds won't be tight. That's what.
Okay, good. Right, so Chebyshev really tells you what's the bounds of probability that some variable is too large. So for example, you could use maybe something like Paley-Zygmunt to show that, well, if you can have a lot of standard deviations with probabilities, but here you're asking to be very, very small, right? So Chebyshev, I guess, is too weak in a
So,
way.
for example, there are pairwise independent distributions where the sum of the variables is almost always 0, except with probability 1 in n.
Yeah, once the fourth term is bounded, you can show the probability of being near 0 is bounded away from 1.
Yeah.
But like
Right.
here it's bounding it close to 0.
So what is this? What does this show?
So this is, I mean, you're saying that you're not too close to 0, which is totally the other way of.
Yeah, the question is how close to 0 you want to be. If you just want to say not very close to 0, you get some bound. But if you really want to say, let's take this and make it much, much smaller, but then you want the probability to go smaller, then you need something, I guess. Actually, I think it's a question. I'm not sure how you can get from tail bounds something about concentration, right? There seem to be orthogonal questions. Maybe the other way, but I'm not sure if you can show something like that.
Chebyshev answers the question of the reverse measure, right?
Yeah.
What's the probability that fx is larger than epsilon?
Where is the concentration though?
Yeah, but you get roughly the same answer for epsilon very small and epsilon over 2 or epsilon squared. Right? It will just be,
So what? I don't understand.
You just say-
if the problem is conceptual or only the
Okay.
fact that it's not tight.
okay.
No, they're two different things. This is showing that you're not concentrated around 0. Chebyshev only says the probability that you're very far from your expectation is small.
Okay. But you can, I see.
And
This
it's
is
only a bound
anti-concentration.
on that probability. The probability could be much, much smaller, right? So you can't.
Anti-concentration and Chebyshev's concentration, so it's two different.
Yeah, exactly.
So here we are assuming that we can assume that expectation of fx is 0.
So we won't have to assume it, no. You can assume it and have some. Actually, if free coefficient is much larger than your variance, you can just by things like Chebyshev, you can show that you won't be concentrated around your average anyways. So, yeah. Okay, so the proof steps, as I said, we'll have. What?
You are writing a bound on the absolute value of f without subtracting the free coefficient.
Yeah, but I mean, it's just assuming the variance of f is, so that's around any point. You can think of it as around any point, or otherwise put, I just shift f by something. It doesn't change the variance of f, and you still ask for this question. Okay. So the proof steps, as I said, will be 2 steps. So one will be to reduce to set multilinear polynomials. So what is a set multilinear polynomials? So f is, let's do it, set multilinear of degree d. If you can partition the variables into d sets, and each monomial is a product of exactly one variable from each set. Okay, so that's a specific family of polynomials. So if you can partition your variables into v1, this joint union up to vd, and your polynomial is just the sum, or some coefficient, okay, sum, so it's I1 in V1 up to ID in VD, so one variable from each set, some coefficient, xi1 up to xid. So we just break dependencies. We just have these sets, and each monomial just have one variable from each set. And once you get to this thing, then you can really use simple induction on those polynomials on the degree. Essentially, you can just kill sets one by one, and this just, I'll show you later, this just reduces to a problem about specific quadratic polynomials. So it doesn't matter what the degree is, you really need to ask questions about quadratic polynomials. Okay, so then 2 is like, well, bound set multilinear polynomials. Good. So that's a plan. So first I'm going to show you how we achieve the first step, and then how we get a bound for set multilinear polynomials. The first step, we're only going to use the fact that we can decompose a normal distribution as the sums of other distributions. So for example, if you sum d normal distribution with variance 1 over d, you'll get a normal distribution. That's everything. That's all we're going to use, essentially, and some convexity arguments. In the second step, we just use some induction and some properties of quadratic polynomials in Gaussians. Okay. Good. Okay, so step 1. So what we're going to use, a technical tool, is going to use a directional derivatives of a polynomial. So let me define those. So what is a directional derivative? Whether if at some point I'm starting to write too small, let me know, because I have the habit of writing too small. So directional derivatives so we choose some direction, y, in r to the n, and we define the directional derivative of f in direction 1. So that's a, sorry, that's in direction y, evaluated on x. This is just f of x plus y minus f of x. Okay? So why do I call it a derivative? Well, because it reduces the degree of f. So if think of y's as constants, and f is a degree d polynomial in x, this will be a polynomial in x of degree at most d minus 1. So one way to see it is that we'll take any monomial and open all the brackets in x and y, and all the terms depend just on x, cancel on both sides. So just get mixed terms, so the degree in x goes down. So for example, so if f is a, so for the purpose of this, sorry, what?
So as in Rn, but not 0, and do you bound the norm?
No, that's a definition.
Why is not 0?
Yeah. So somehow these type of definitions come from polynomial finite fields, which are more natural, but they seem to be also applicable here over real polynomials. Good. So let's start with a simple lemma. And also for this part, just So I won't have to carry about like having variables of degree larger than 1, then asking about coefficients of the moments, and then going some Hermat basis. Let's just assume that f is multilinear, just meaning that each variable occurs with degree at most 1. Okay, so this is just something to make the calculation slightly simpler. So let's start. So here is a simple lemma. So we're going to derive f several times. Okay, so let me first make a definition. So the derivative of f in directions y1 up to yd is just what you think. We'll just derive it in direction y1, and then y2, and y3, and so on. So the degree will go down and down, right? And if you want to write it explicitly, well, here it was just a subtraction of 2 terms. Here you'll have 2 to the d terms. It just be the sum over all subsets of d. You have some coefficient here. And then f of x plus the sum of yi, I in I. So that's just, if you really open in brackets these derivatives, right, so here we have a term minus another term, so we're subtracting 2 terms. If you do d terms, we need to subtract or add 2 to the d terms. So there's some simple calculation. But the point is that, well, if f was a degree d polynomial, that's now a constant polynomials. So it won't no longer depend on x. So the lemma says, well, the derivative of y, so let's just call g y1 to yd to be this derivative. So the derivative of y1 up to yd of f of x. Okay? So first, g doesn't depend on x. So although it's defined depending on x, it really is not dependent on x. So you can really write as g of y1 up to yd. And the reason is, well, we said derivation reduces the degree by 1 at every step, right? So if we reduce the degree d times, this is either a constant or let's say it's identically 0. Anyway, its value does not depend on x. So, and also, but notice that g, another thing will be that g is set multilinear. Multilinear in y1 up to yd. So here we have n d variables. We're going to break them into those d sets. And actually, I'll show you in a second that, well, what fell down? Not sure. G will just have each monomial of G, we just have one variable in each y1, y2 up to yd. Okay, so actually there is a very simple formula for it. But in the third thing, so that's second thing, and then the third thing, I guess, would be that the variance of G is not too small. At least the variance of fd, where fd, that's just the degree d part of f. Okay, so here we're just taking all the monomials of degree exactly d. Why are we doing that? Because, well, any monomial in f of degree less than d is going to, if you derive it d times, will be identically 0. So it can never influence g. But every monomial of degree exactly d will influence it. So I'll show this in a second, just a few lines calculations. But let's just show what do we get from it. So
Is this for most y's or for any y?
for any y. This will just be a polynomial in y1 up to yd. So what we're going to get here, we're going to get it, well, it's still not clear why we're doing it, but at least we got some set multilinear polynomial that depends on f and has variance not too small. We need the variance not to be too small because obviously if the variance is tiny, it can be very close to 0. So we need to assume something about the variance not being too small.
So what is this variance over?
Which one? This?
What is the randomness of
Y. So here y1 up to y, good. So here y1, this just means y1 up to yd are going to be also normal to the n. The same distribution that we had before.
or the side of fd?
And the same thing. So here this will just be a polynomial in x, and here x will be n independent normal variables. Good. Okay, so that's going to be one lemma. And then the second lemma will say, well, it's enough to get bounds on G to get bounds on F. So it will be, let's say, lemma 1. And lemma 2 will be, well, the probability that f of x is smaller than epsilon, you can bound it by the probability of g of y1 up to y1 up to yd being smaller than some constant times epsilon. Here I'm hiding some constant depending on d, something like d to the d, but whatever. Root 1 over 2 to the d. So that's the important part. We're going to lose here. So that's one case where we lose exponential powers. We're going to lose another one when we're going to bound the set multilinear polynomial. So we're going to lose this twice. Okay. Yeah.
Do you know what the correct anti-concentration bound for set multilinear Gaussian polynomials is? Thinking for 2 seconds, I couldn't see how to get something even as bad as epsilon to 1 over d.
It's a good question. I thought about it, I'm not sure.
Could be epsilon as far as we know, right?
Maybe. Yeah.
What was the question again?
If you can get just for set multilinear polynomials, is the right answer epsilon to the 1 over d, or is it maybe epsilon? We know that for x to the power d, that's normal to the power d, is the answer of being close to 0 with epsilon to the 1 over d. But that's not set multilinear. Maybe if we make it set multilinear, but again, maybe you do the trick that you said, right? So take x, write it as a sum of x1 up to xn.
Multilinear, but won't become set multilinear.
I see, you're right. Okay.
So I don't know.
It's a good question. Right. Okay. So again, so given those two lemmas, this will just allow us to reduce the question from studying the probability that f is concentrated too nearly to 0, that of g. Good. So let me now show you roughly how we prove those two lemmas, and the proofs are so this will be some calculation. Here we'll use some convexity argument. So let's do it, I guess, here. Or maybe there. So if I write here, can people see it? Can you see it? I'm writing here? Yeah? Okay, good. So let's start with lemma 1. So let's just calculate what g is. So well, derivatives are linear, right? So we can just calculate it for a monomial and see what we get, then we can sum it over all the monomials of f. Okay? So let's say lemma 1. So assume some monomial, so m of x is xi1 up to xik. Let's say x1 up to xk, to be simpler. So what is this derivative? So, well, if k is smaller than d, then this derivative, y1 up to yd of m, is just identically 0. So I already said that. Well, the derivation reduces the degree by at least 1 at every step. So if we start with polynomial with degree less than d, and we derive d times, the degree will now, it will be just an identically 0 polynomial. Okay? Now, what if x is equal to d? So let's say, there's a lot of stuff in here. So if k is equal to d, well, then it's just some calculation. You can show that what you'll get is that the derivative of y1 up to yd of m is just, so you're going to sum over all permutations over those d elements, and you're going to have y1, let's do it, let's say those were i1 up to ik. So you get y, let's say sigma 1 i1 up to y sigma d id. So again, what do we have here? So here we had this product of xi1 up to xid, in the k equal d part, and we're going to have exactly that, except each variable we're going to come from one of the yi's. Okay? So it might be that the first one comes from y1, the second from y2, and so on. But this is symmetric, so it can come in any order. Okay? So this is just some. So I guess, so now if you want to ask, okay, so this proves that g doesn't depend on x, and that g is set multilinear, right? Because now each monomial just have one variable from each of the yi's. Okay, so we verified 2 of the 3 claims. For the variance, you also get the same. So the variance of that would just be the sum of all the coefficients squared, but each coefficient in f, d, like the part of degree d, is a monomial of degree d. It will contribute a coefficient here. So actually, if you really want to get good bounds for multilinear, actually you'll have here this is just going to be equal d factorial times z. So it'll just be much larger. But if it's not set multilinear, you get some worse bounds. Where we assume it's multilinear, well, if it's not multilinear, you need to replace this degree d part by degree d in the Hermite basis part. Hermite basis is just a set of polynomials which are orthogonal under the normal distribution. So this is some slight technical thing. It's not very interesting.
But for that, you actually need this. You're saying that what you're going to get in the end is more general because you don't. But you still need a normal distribution somewhere.
Yeah. So here I need to assume anything. So okay, for any distribution, you need some bound on orthogonal polynomials in it. So, but it will be something dependent on d, right? So that is just be, if you think of d as a constant, which is just some constant. So I think some of the more interesting part is what's the power, what's the polynomial in epsilon that you get, not what's the coefficient depending on d that you get here. I think if epsilon is very small. Okay, so that's the first lemma. Okay, how do we prove the second lemma? So where would I write it? Let's do it here. No, let's start here. Good. So let me start with a convexity lemma. And it says the following thing. So choose any distribution, d, and choose variables for this distribution. So choose, let's call them w1 up to wd, and let's say z1 up to zd, coming from some distribution d over the reals. Okay, so that's some distribution. And we're going to look on all the partial sums where every time we take either w1 or z1, w2 or z2, and so on. So for every, let's do it for every I subset of d, let's define, I don't know, how should we call it? X, maybe X, let's call it R. So R capital I is just going to be the sum of all wi, I in I, plus the sum of all zi, I not in I. So every time you're summing either w1 or z1, either w2 or z2, and so on. And we have 2 to the d such options. And the claim is that, well, okay, let's lift it up. And the claim is that those distributions are somewhat positively correlated in a very strong sense. So let's choose some subset S of Rn. Let's say some measurable subset. Then the probability is that also for all I in D, all these variables Ri lie inside the set S, well, it's larger than what you'd expect if they were truly independent. So it's larger than the probability that, let's say, just one of them, let's say W1 plus WD lies in S to the 2 to the D. Okay, so again, so what do we have here? We're choosing those highly correlated random variables, and we're asking what's the probability that all of them lie inside some set S, and that's they're positively correlated in the sense that this probability is larger than the probability that if they were truly independent, they would lie in the set S. Which is the same as one of the, so all of them are identically distributed, just one of them is S to the power 2 to the D. Okay? So let me just show it for D equal 2. Then this is just applying Cauchy-Schwarz iteratively. There's nothing deep here. So for D equal 1, let's just see just equality. D equal 1, you mean here I'll have, you want W1 in S and Z1 in S, right? So that's just independent. So let's do the D equal 2 case. So let's just define a function f of WZ to be 1 if W plus Z lie in S, okay? So maybe we add half, let's call this H. So what do we have here? So we just have, so what is the left-hand side? This is just the average over H W1 Z1, H W1 Z2, H W2 Z1, H W2 Z2.
So in the definition of H
That's in good. You're right. Sorry.
Why do you call this convexity?
So I'll show you in a second. Just Cauchy-Schwarz. I haven't applied convexity yet. Okay, so but we agree that the left-hand side is just exactly that. Good. So here's another way of writing it. That's the average over W1, W2, and Z, H of the average of Z, H W1Z, H W2Z squared. Right? Just opening brackets get Z1 and Z2. And that's at least, well, the average over W1, W2, and Z, H of W1Z, H of W2Z squared. So here we applied convexity. Or Cauchy-Schwarz, or whichever you want to call it. Okay? And now if you do it again, so now you'll pull Z out and do it for W1 and W2, you'll get exactly here sum to the fourth. Okay, so I'm not going to do it, but just do it the same trick again. Good. So okay, so we have this lemma, so let me just write it here and then so we said that for every S in R, the probability that for all I, Ri is in S, is at least the probability that one of them, let's say R not, is in S to the D. Good. So how do we apply it here? Well, so let's just S be the set of all x's where f of x is at most epsilon. Okay, so that's going to be our set S. And so what do we have? So let's read what we have here. So we have the probability that f of x is at most epsilon. Let's say to the 2 to the d. So I'm raising this equation to the power 2 to the d. So that's the probability that for all I, f of w, it's sum of wi, I in I, plus sum zi, I not in I, is smaller than epsilon. Good. Right? So that's just reinterpreting what we had there for this specific set S. Now let me make some definitions. So we're going to choose x to be W1 plus WD. We're going to choose y to be Wi minus Zi, and we'll need some normalization here in a second. And we're going to choose this distribution D to just be normal 0, 1 over D.
Is this yi?
Yeah, so that's going to be yi. So actually, we need some normalization here, but we'll get it in a second. So let us see what we have here. So we choose this distribution. We're using the fact that if we sum this distribution D times, we get a normal distribution. So x is normally distributed, right? And each of the yi's by itself is normally distributed 0 and actually 2 over D. So we need some factors later. And so importantly, each of the yi's is independent, right? X is dependent on the yi's. But remember this polynomial g that we had no x in it, so it won't matter that x is dependent on the yi's. So let's do it more formally. So we have this. So here's another way of writing it. So I'm going to claim that this is just x plus the sum of yi, I in I. Maybe for that I needed to have zi minus wi here. I'm not sure. All right, so if we take x and we sum all the yi's, we're going to get exactly this part. Okay? So here's one way to bound it. Well, we know that if we sum f on those with plus or minus signs, we get the derivative of f in direction y1 up to yd. So that's this definition of the derivative. So that's at most a probability that if we sum minus 1 to the d minus I f of x plus some yi most 2 to the d times epsilon. Right? Definitely, if all of those are smaller than epsilon, anyway, then I'm going to sum them with signs. They're going to be at most 2 to the d times epsilon. Right? So the way I'm going to sum them, so this would just be this g of y1 up to yd. These polynomials that we had. Okay? So this allows us to reduce from arbitrary polynomials to this g, which is a set multilinear polynomial. Okay? Actually, there's a tiny point here where I need to change, where we need to normalize yi's by something to make them also normal. But since g is multilinear, set multilinear, we just normalize by multiplying g by some constant. Because each monomial just have exactly one variable from each one of the yi's. So again, so here what we had here, x, so y1 up to yd are independent. X is normal, but x and y up to yd are dependent on each other, right? So they're highly correlated. But what we need to fact that g doesn't depend on x at all. So it doesn't matter.
I think I should get a d to the d factor or something?
Yeah, so we get something like d to the d over 2, something like that, yeah. Good. So that finishes this part, right? So we had that if a polynomial, so we can reduce bounding for f to bounding its derivative polynomial, and its derivative polynomial, now we just need to derive its derivative polynomial, or any set multilinear. Okay, so let's show you how you do that. Good, so I was trying to cheat, but it got me. Good, so what we said is that the variance of g is just equal, or up to some constant equal, to the variance of the degree d part of f. So if most of the weight of f is on the degree d part, or some significant fraction, then we're done. If not, then just the degree d part is very tiny, so it won't influence at all. So you just assume it's tiny and just do it for d minus 1.
But then you can sort of balance out the weight all across it, and you have no significant level.
So one of them will just 1 over d, right?
Does that suffice to?
Yeah, it suffices. Just a constant. Think of this as a constant. So just some constant. One of them has a constant fraction of the measure.
So what is the argument that the variance is greater?
What?
That the variance of g is greater than?
Okay, so good. So what we had was that we said that the variance of g is at least the variance of fd, where fd is a degree d part of f. So again, what Zev said justifully is that what happens is the degree d part has only a tiny fraction of the measure, right? So actually you can say, well, let's assume that the variance of f to the d is at least some epsilon to, let's say, I don't know, 10, I don't know. It's some constant polynomial in epsilon. Let's say we don't really care to be tight. Then we can also apply it here and get something which is good enough for us, right? Or if it's so small, so here will just be done, reducing to g. If it's so small, then with very high probability, 1 minus polynomially small in epsilon, then fd is tiny, right? It really does influence this polynomial by a lot. So we just say instead of bounding it with epsilon, just bound it with something much smaller.
So my question was, what is the argument for the first one, variance of g?
Which one?
Yeah.
This one? This one?
No, the first.
Oh, this one we said just this calculation that well, each coefficient in fd appears as d factorial coefficients in g. So the variance of this is just, well, in the multilinear case, just d factorial times that. When it's not multilinear, there is some losses, but still always greater than that. Okay. Good. So now let me show you how can we handle set multilinear polynomials. And the point is that for set multilinear, you can just use induction as a degree and just kill variables one by one, or sets of variables one by one, in a very simple way, which maybe is not optimal, but you can get epsilon there. But that's, since we already lost an exponential factor, that might as well lose it again. Right, so we have, let's say, we have this polynomial, so we have So let's say we have this g of y1 up to yd. And you want to bound the probability that this is at most epsilon. Okay, so let's just think of fixing the last set. Okay? So let's just call, I don't know, h of z. That's going to be a set multilinear in d minus 1 variable, which is just going to be this g where y1, yd minus 1, and z. So we're just fixing the last set of variables to some specific constant and looking at this polynomial in degree d minus 1. So what's this probability? Well, this is just the average over z, the probability that hz, y1, yd minus 1 is smaller than epsilon. Right? Same thing exactly. So, but here, well, at least if the variance of h of z is not tiny, we're done, because we just use induction for d minus 1. So the only bad part that can happen is if this polynomial has very, very small variance. Right? We agree? Right. So we can say that this is, let's say,
You mean for fixing of z?
yeah. So we fix z. We look at this polynomial. This is polynomial d minus 1 times n variables.
There are two types of z, one for which the variance is large and one for
Exactly. Exactly. So you can just bound it, but let's say the probability that the variance of hz is, let's say, below square root epsilon plus, well, what you get here for d minus 1. So by induction, so let's say we're going to prove that this is something like epsilon to the 2 to the d times some order of epsilon to the d. So this is going to be plus the probability, let's say, for good z's. So again, what?
Order of epsilon to the 2 to the minus d.
Yes, you're right. Thank you. Yeah, good. Yeah. Plus the probability for good z. So here we just use induction for d minus 1. So it will be, let's say, root epsilon to the 1 over 2 to the d minus 1, and that's what we're going to get. Okay. So then now we just have the question of what's the probability of the variance of this polynomial being very small. Okay. Then you just need to bound that. So let's just see what is this variance. So what is hz? So hz in y1 up to yd minus 1. So what we have just a summing of y1, I1 up to id minus 1. And we have the, so what's the coefficients here? So we're going to have the sum over, let's say, j, y, I1, y1, I1, yd minus 1, id minus 1, and here this z, j, right? So for each monomial, we're summing over all zj's. And times obviously the coefficient of f I1, id minus 1, j, right? So what's the variance? Well, we're just going to take, for each I1 up to id minus 1, we're just going to look on all those coefficients for any possible value of the last variable, and just going to look what the average is, the average of the squares. So what's the variance of hz? Well, just the sum over I1 up to id minus 1 of the sum over j, f I1, id minus 1, j, zj squared, right? We agree on that? So what do we have here? So that's really that's a quadratic polynomial. It's quadratic in z. So we just need to ask for a quadratic polynomial, what's the probability that it's very small? Actually, that's a specific quadratic polynomial. So actually, you can write this also as z transpose az, where a is positive semi-definite and has trace 1. So let me convince you by that. So what do we have here? So this is just another way of writing is just think of this as this is some linear combination of z, right? This is some vector ui1 up to id minus 1 inner product with z. Well, this vector is just a vector of the coefficients of f for all values of the variables in z, for all values of j. Okay, good. So this is just the sum of those squares, and these variables are just contain all the coefficients of our polynomial f or g. Right? So the sum, let's say the variance is 1, so the sum of the squares of all those is 1. So another way of writing this is just the sum over ui, so u capital I, z squared, where the sum of those squared is 1. Just assuming that the variance for polynomial is 1. So this matrix is just going to be the sum of ui transpose, or maybe ui transpose. Right? This is a positive semi-definite matrix just representing this and has trace 1. Good. So why is it useful for us? So we're really asking not for a generic quadratic polynomial, but what we're asking? We're asking, take your random variables, in a way, rotate them to be in this set of coordinates, and then ask what's the probability of being roughly in a small ball. Roughly, not exactly, but roughly that's what we're asking here. So in general, it's some property for distribution of some quadratic polynomials. But for normal variables, we can cheat, because normal variables are invariant under rotations. Right? So the probability, let's just do it maybe here. So again, so what we're asking is, what's the probability that Z transpose AZ is at most, let's say, epsilon, where this is a positive semi-definite matrix and has trace 1. But then we can rotate things that exactly, so let's assume the eigenvalues here are lambda 1 up to lambda n. This is just the same question as what's the probability that the sum of lambda I zi squared is at most epsilon, where z's are normal to the n. Here we just use the fact you can diagonalize it by an orthogonal transformation. This maintains the normal distribution, so we get this very simple question. And for general distributions, it's somehow a question how well the distribution is centered around 0 under orthogonal transformation. I don't know, but we're not using low concavity here. And that's just a routine calculation, so I'm not going to do it here. So that's just like a order of something like root epsilon. So obviously, so if you just add z1 squared, then this probability is root epsilon, right? And you just do some simple calculation to show it. So this is always the case. I'm not going to do it. Yeah, obviously you're using the sum of lambda I is 1, right? Yeah. Which is the same assumption as the variance of your original polynomial being 1. Obviously, if you make the variance very, very small, it can be very, very small. Good. Okay, so that basically wraps up the argument. So let me just recap it. So the first step was to reduce from general polynomials to set multilinear polynomials. There we had this loss of 1 over 2 to the d because we used this convexity argument. We chose these 2 to the d dependent distributions and show that they have positive correlation of line inside any set S. And then we just did some simple calculations for set multilinear polynomials, which maybe are not tight. Maybe for set multilinear, the right answer is epsilon, not epsilon to the 1 over d. And that's it. Thanks.
So I'm slightly confused because initially you said that part of the point of this is that it works for non-normal distributions.
Mm-hmm.
Yet here you invoking normality.
Yeah, obviously. So here, so what would you have for general distributions? What would you have to ask? What's the probability? I give you any distribution. What's the probability of that, right? Of the specific quadratic polynomial being small. So we're not even asking for general quadratic bound, but for specific. So you reduce degree d bounds to quadratic bounds.
Can you say that the distribution has the property that if you rotate it, then none of the coordinates get too much of the mass of the set? No coordinate coordinate is much larger than the other coordinate.
Okay.
It's exactly the same thing, right? You're looking at some ellipse, which is some quadratic form of the.
Yeah.
Yeah.
It's exactly.
It's more general than normal.
But how general is it?
Good. So I don't have any good examples. So the distributions people usually look at are either normal or log concave because
Also notice, like in
or discrete, and this is not discrete distribution.
in
we look for
previous
here. Yeah.
somewhere
Yeah.
up there, when you do this y is equal to zi minus wi,
Yeah.
you're assuming the difference of two normal variables is normal, which is true, but if it's not normal, then you have to, there's some.
Yeah, I agree. So
bounds
in the normal case, everything is simpler. In the general case, you need to ask, okay, what type of what we need for distribution? So we need to be the sum of d distributions.
So for example, if
Yeah. And then this bound you need for the difference of two of these distributions. So in general, what you'd have, you had some basic distribution. Let's call it d1. And the proof will work for dd, which is d1 summed d times, right? So, and you'll need this, let's call it, I don't know, quadratic bound for d2. Okay? The difference, let's say this is d1 minus d1. Let's assume d is symmetric, maybe, or whichever, for d1 minus d1. So you take any distribution that you want, and you'll prove some anti-concentration bounds for this distribution, convolving itself d times for the greedy polynomials, assuming that you have some bound for the difference of it with itself for quadratics. Okay, so this could work for discrete distributions as long as you have these properties.
Actually, an interesting